In late 2024, a $40 billion chip factory rises from Arizona's desert, aiming to recreate the magic of TSMC's world-leading Taiwan fabs. The stakes are high. This is where chips for iPhones and AI supercomputers will be born. Yet early on, engineers faced a baffling dilemma. The facility had to import ultra-pure sulfuric acid from 6,500 miles away in Taiwan. American suppliers couldn't meet TSMC's standards, and local chemicals cost 5 times more. Even Intel, the veteran US chipmaker next door, jumped in to buy from these overseas shipments, a fact TSMC's CEO relayed with incredulity. "How did you live before?" "It was very hard before, but now you are here," he recalls Intel saying. This real scenario reveals a deeper mystery. Why is it so hard to duplicate a cutting-edge semiconductor fab on US soil? In theory, a chip plant is a marvel of precision engineering that should be reproducible anywhere. In practice, every tiny variable, from the brand of pump to the length of a pipe, can throw off the delicate process. The industry mantra is copy exact, meaning every detail must mirror the original fab to achieve predictable results. So when Taiwan Semiconductor Manufacturing Co. tried to clone its advanced factory in Phoenix, they encountered a storm of unforeseen challenges. This is the story of TSMC's attempt to copy-paste its success overseas, a story of smooth silicon dreams colliding with desert realities. We'll explore why a company that perfected chip making in Taiwan finds itself with a lot of snot, tears, and all kinds of training in Arizona. How do geology, water, and air in the American Southwest complicate processes measured in atoms? Why does a thriving supplier ecosystem in Asia prove so hard to replicate in the US? And what do these struggles mean for America's bid to onshore critical chip production? TSMC, Taiwan Semiconductor Manufacturing Company, is the world's most advanced chip foundry, fabricating processors for Apple, Nvidia, and many others. In the semiconductor realm, yields are king. Yield refers to the percentage of chips on each silicon wafer that emerge flawless. A fab can churn out thousands of chips, but if even a speck of dust or a minor process variation causes defects, many of those chips become worthless. Modern chips pack billions of transistors in areas smaller than a fingernail. Even a 4-nanometer wide particle can ruin a chip. High yield is critical because each wafer costs a small fortune. A single 300mm wafer at 5 nanometers can cost around $17,000 to produce. When yields slip, those costs explode. As one engineer puts it, "Making a wafer is the most complicated manufacturing process in the world. I can't imagine anything else more difficult than this. It involves up to 4,000 precise steps with no room for error. The goal is to perfect those steps and repeat them exactly, over and over, wafer after wafer." This is where the copy-exact philosophy comes in. Pioneered by Intel and embraced in spirit by chipmakers worldwide, copy-exact means that when you build a new production line or fab, you replicate every possible parameter from the proven facility. Same equipment models, same process recipes, same materials, down to using the same brand of valves, pumps, and filters, and even duplicating the lengths and routing of pipes and wires. Why such obsessiveness? Because even trivial changes can produce different results at the nanoscale. The semiconductor process is a finely tuned orchestra. Swap a violin mid-performance, or a chemical supplier mid-process, and you might throw the whole symphony off key. Intel has credited its copy-exactly program with minimizing risk in new fabs. Since all factories use similar equipment, the copy-exactly process minimizes the risk of introducing errors when ramping up production. In other words, if you've perfected a recipe in one kitchen, you'd better rebuild an identical kitchen to get the same dish again. For TSMC, which leads the industry in chip yields and process technology, copy exact is an article of faith. It's how they achieve remarkable consistency. In 2020, TSMC boasted its new 5-nanometer process hit defect rates around 0.1 per square centimeter within months, meaning only one defect in a billion transistors or so. High yields translate directly to profit and production capacity. A few percentage points of yield can make or break a chip's economics. Conversely, a yield problem can cost astronomical sums. A sobering example. In 2019, a single batch of bad photoresist chemical at TSMC's Fab 14 went undetected until wafer yields came out far below normal. By then, thousands of wafers were contaminated. TSMC had to scrap an estimated 10,000 to 30,000 wafers, eating a loss of about $550 million in revenue. One foreign polymer in a chemical, one tiny flaw, cascaded into over $500 million of damage. This incident hammered home the point. Vigilance over process consistency isn't paranoia, it's survival. So when TSMC agreed to build an advanced fab in Arizona, producing 5-nanometer class chips, later adjusted to 4 nanometers, for American customers, they knew the only way to succeed was to copy-exact their Taiwan operations. The Arizona fab, designated Fab 21, would be modeled on TSMC's cutting-edge facilities in Taiwan's Tainan Science Park. In theory, TSMC tried to transplant not just the machines, but the entire manufacturing ecosystem that makes those machines hum. Yet, almost immediately, theory met reality. TSMC's leaders candidly admit they underestimated what they were up against. Building the same fab on a different continent turned out to be far more complex than copying a blueprint. Before we delve into the hurdles, let's frame why this duplication is so strategically important. The US government, via the CHIPS Act, is investing $52 billion to onshore semiconductor manufacturing. Washington's goals are part economic, jobs and tech leadership, and part geopolitical, reducing reliance on Asia's chip hubs, especially Taiwan, which lies under constant shadow of potential conflict. TSMC's Arizona project is a flagship of this effort, supported by an estimated $6.6 billion federal grant and other incentives. If TSMC can make top-tier chips in America at scale, it would bolster US tech sovereignty and mitigate the single point of failure risk of having so much capacity in one small island. But if the Arizona fab struggles to meet the quality or output of its Taiwan siblings, it raises tough questions. Can the West really rebuild a self-sufficient semiconductor supply chain? Or are decades of specialization and clustering not so easily unwound? With that context, let's explore the key technical and engineering challenges, the variables that differ between TSMC's Taiwan fabs and their attempted clone in Arizona. From the ground beneath the fab to the air and water that flow through it, from the availability of ultra-clean materials to the training of its workforce, we'll see that copying a fab exactly is far more than shipping over some machines. It requires copying an entire environment and culture. As we unravel each challenge, the central mystery unfolds. Why is it so hard to duplicate a TSMC fab in the US? And what does that say about the future of a globally interdependent industry? Building a chip fab is not like building a typical factory. It's more akin to constructing a giant scientific instrument. These facilities are exquisitely sensitive to vibration, temperature, humidity, and contamination. Geology matters. Fabs need geologically stable ground with minimal risk of earthquakes or even subtle tremors that could disturb alignments. Chip manufacturing operates on tolerances of a few nanometers, billionths of a meter, especially in lithography, where a misalignment can ruin all the chips on a wafer. In Taiwan, TSMC has learned to mitigate frequent minor earthquakes, for instance, using deep foundations and vibration dampers to isolate tools. Arizona, on the other hand, is geologically quiescent. It's not on a major seismic fault. In fact, this was one attraction. Beyond water, chip fabrication requires geologically stable ground, low humidity, and a positive business climate, notes Paul Westerhoff, an Arizona State University engineering professor. By that measure, the desert north of Phoenix is ideal, solid bedrock and little natural shaking. But being stable isn't enough. The site must also be prepared to absorb man-made vibrations from nearby roads, construction, etc., and support extremely heavy equipment. A single EUV lithography machine, for example, weighs over 100 tons and uses lasers so sensitive that any vibration can blur the microscopic circuits it draws. Arizona's site had to be graded and its fab foundation meticulously engineered for this task. Water is another silent factor. Fabs slurp tremendous volumes of water to achieve the required cleanliness. Semiconductor manufacturing demands ultra-pure water UPW to rinse wafers after various process steps. Ultra-pure means water stripped of every mineral, every ion, virtually every molecule that isn't H2O. It's often said this water is so pure it's unsafe to drink, as it would leach minerals from your body. Each wafer might be washed dozens of times through its fabrication. A modern logic fab can use millions of gallons of water per day, enough to supply a small city. That sounds incompatible with an arid region like Arizona, which faces chronic drought. Indeed, observers scratch their heads. Why build such a water-intensive plant in the desert? TSMC, conscious of this, pledged advanced water recycling. In Taiwan, during a drought, TSMC has even trucked in water to keep fabs running, so they know water risk well. In Phoenix, they are building a state-of-the-art industrial water reclamation plant on site. TSMC Arizona says it will reclaim about 65% of the water it uses, with a goal of eventually reaching near 100% net zero water use. Essentially, they plan to treat and reuse wastewater for cooling and other non-process uses, and possibly even repurify some of it back into UPW. This approach, known as zero liquid discharge, means almost no wastewater leaves the facility. It's costly. Fabs in Arizona voluntarily do zero liquid discharge. It costs them a lot more. But they do it because it is part of operating in the desert, Westerhoff explains. Over time, these conservation measures can make Arizona's fabs among the most water-efficient in the world. Ironically, being in a water-scarce area is spurring innovations that could set new standards globally for water recycling. However, not all water challenges are purely quantity-based. Water chemistry differs by locale. The raw municipal water in Phoenix has a different mineral profile than Hsinchu's or Tainan's water. This affects the filtration and purification process. TSMC essentially built a duplicate ultra-pure water plant in Arizona, but slight differences in input water could mean tweaking the treatment stages, more filtration here, different membrane there, to reach the same purity. Moreover, once purified, the water must stay pure through miles of piping, an area where the copy-exact philosophy kicks in. If the Taiwan fabs use stainless steel pipes of a certain grade and length, the Arizona fab would try to use the exact same to avoid unexpected leaching or contamination. This level of replication can be surprising. It's not just the big tools, but even piping materials and lengths that matter. In the end, after intensive effort, TSMC is confident its Arizona water treatment system can deliver equally pristine H2O. They will need it. Each chip layer, and there are 20, 30 or more layers, must be rinsed to atomic cleanliness. As Westerhoff describes, modern chips have features so small, on the order of 4 nanometer gaps, that even the smallest particle can get stuck and ruin the semiconductor. That's why thousands of gallons of UPW are used to wash away every last speck of particles and chemicals at each step. Then there's the air. Arizona's air is famously dry and generally very clean in terms of man-made pollutants. Low humidity is actually a boon. Moisture in clean rooms can cause unwanted reactions or allow trace contaminants to travel. In chip lithography, too much humidity can interfere with photoresist chemistry. So the desert's dryness helps. But Arizona has its own phenomenon: dust storms. Seasonal haboobs can send clouds of fine dust sweeping through Phoenix. Fabs are sealed with advanced HVAC systems and filters, of course, but a massive dust storm is a test of those defenses. The clean room must maintain ISO Class 1 conditions, no more than 10 particles of size 0.1 micrometers or larger per cubic meter of air, exceedingly clean. Outside, a desert wind can carry thousands of particles per cubic meter. Thus, the facility's intake filtration and positive air pressure systems have to work overtime. It's not an insurmountable issue. Fabs have existed in desert environments. Intel has run fabs in Arizona for decades without incident, but it requires vigilant maintenance of filters. Air quality control is part of the hidden art of fab operations. Cleanroom contractors from Taiwan were brought in to ensure the Arizona fab's airflow and filtration match TSMC's specs. These companies, like UIS and others, have been busy. Orders for cleanroom systems have surged as TSMC and others expand overseas. In fact, TSMC's Arizona fab is roughly double the cleanroom size of a typical logic fab, indicating how much infrastructure is being built to keep dust out. Cleanrooms are designed to eliminate dust, airborne particles, and other contaminants that could damage sensitive components. An absolute must when features on chips are far smaller than a single dust particle. Temperature is another factor, albeit easier to control with brute force HVAC. The desert sees scorching heat in summer, but the fab's climate control doesn't really care what's outside. It will cool and dehumidify the incoming air, regardless of 115-degree Fahrenheit temperatures. The bigger issue was ensuring power stability. The fab will draw on the grid plus backup generators. Arizona's electric grid is stable, though heavy monsoon storms occasionally cause outages, and chemical and gas delivery infrastructure. More on that in the next section. In short, from a physical environment perspective, Arizona is not a bad location for a fab. It's seismically calm, dry, and has abundant land. TSMC's site is a sprawling 1,129-acre campus in North Phoenix, with plenty of buffer zone. Yet, it's all the subtle differences, the water, the air, the local building codes and permits, as we'll see, and even the soil, that mean a copy fab can't ever be 100% identical. As one TSMC manager analogized, running the same process in a new place is almost like when you bake a cake at high altitude versus low altitude. You're still baking the same cake, but you have to make some fine-tune adjustments. In Taiwan's recipe, they know exactly how the cake rises. Arizona is a high-altitude kitchen, figuratively speaking, and it's forcing them to relearn those fine adjustments. Beyond the bricks and mortar of the fab itself, one of TSMC's biggest challenges in Arizona has been rebuilding its supplier ecosystem from scratch. In TSMC's home base, Hsinchu and Tainan, Taiwan, there exists an extensive, dense web of suppliers and contractors that collectively support fab operations. Within a short drive of TSMC's fabs are companies that provide ultra-pure chemicals, specialty gases, silicon wafers, spare parts, sub-tool components, maintenance services, precision cleaning, and waste management, essentially every little thing a fab might need, often on a just-in-time schedule. This ecosystem didn't appear overnight. It's the product of 30-plus years of Taiwan's semiconductor industry growth. Many of these suppliers are accustomed to meeting TSMC's exacting standards. Some, like gas suppliers, even run pipelines directly into the fab complexes. So when TSMC builds a new fab in Taiwan, it can easily tap into this network and know that the critical materials will arrive with the right purity just in time. And if a tool breaks, a local technician or spare part is close at hand. In Arizona, by contrast, TSMC plopped down a leading-edge fab in what was, until recently, open desert. The Phoenix area does have some semiconductor presence. Intel's massive campus in Chandler, some ON Semiconductor and NXP legacy Motorola facilities, but it lacks the complete ecosystem for cutting-edge nodes. Many of the chemicals and materials required for 5 nanometers per 4 nanometers processes simply were not produced in the US at the necessary purity or volume. TSMC discovered this quickly. C.C. Wei, TSMC's CEO, recounted that American chemical suppliers cannot produce the grade that TSMC needs, and if they tried, the price was exorbitant, 5 times higher than in Taiwan. One striking example was sulfuric acid, a common yet vital chemical used in cleaning silicon wafers. Rather than rely on subpar or overly expensive local supply, TSMC chose to ship high-grade chemicals from Taiwan. "We transport sulfuric acid from Taiwan to the LA port, and then truck it from the port to Arizona. Even this is cheaper than doing it in the United States," Wei said. Think about that. Barge tanks of acid across the Pacific and hauled by truck 400 miles inland, and it still beats the local option. This highlights how optimized and low-cost the Asian semiconductor supply chain has become, and how challenging it is to replicate that in America. The situation with sulfuric acid was not unique. Other specialty chemicals, developers, etchants, gases like neon and xenon, etc., and even raw silicon wafers often had to be imported. Over the past 2 years, a number of TSMC's key suppliers have announced plans to set up U.S. operations, often in Arizona or neighboring states, to support the fab. For instance, Sunlit Chemical, a Taiwanese company, opened a plant in Phoenix in late 2024 to produce high-purity chemicals locally. Industrial gas suppliers, filtration companies, and equipment component makers, in total about 14 key suppliers, have committed to establishing facilities in Arizona, creating a mini-cluster around TSMC. This is a positive development. It shows the clustering effect in motion. The Greater Phoenix Economic Council noted that since TSMC's announcement, 39 semiconductor-related companies have relocated or expanded in the region, bringing over $37 billion in investment. In time, Phoenix might build its own robust semiconductor ecosystem. But these things take time, often years to build plants, train workers, and reach the quality levels required. In the interim, TSMC must deal with a supply chain that is longer and more fragile than what it enjoys in Taiwan. Longer supply lines mean more inventory must be kept on hand as a buffer, which ties up capital and complicates logistics. If a chemical is coming by ship from Asia, TSMC can't get it on a few days' notice. They need to plan months ahead and stockpile, or pay to fly material in at great expense for emergencies. The just-in-time rhythm is disrupted, and when something goes wrong, it can become a crisis. Imagine if a shipment of a critical gas gets delayed at the port. The fab could literally run out and halt production, an almost unthinkable scenario in Taiwan thanks to local supply redundancy. Another major gap: equipment maintenance and spares. Chip fabs rely on incredibly complex machinery. Think ASML's 150 million EUV scanners, and a myriad of supporting tools. In Taiwan, equipment vendors like ASML, Applied Materials, Lam Research, etc., have local offices and parts warehouses near the fabs. Many second-tier tool firms and third-party service providers are also nearby. In Arizona, some of that exists. ASML, for instance, has a presence to support Intel's fabs. But ramping up a fab requires a small army of vendor field engineers and a supply of spare parts. TSMC ended up bringing hundreds of experienced technicians from Taiwan, both its own staff and supplier engineers, temporarily to Arizona to install tools and train the local team. This became a point of cultural friction, which we'll discuss later, but it was unavoidable. Without the seasoned experts, the highly calibrated tools could not be brought online as efficiently. Copying a fab means copying the know-how, not just hardware. TSMC essentially transplanted a slice of its Taiwan workforce to Phoenix to duplicate the tacit knowledge of running these machines. Yet another wrinkle: U.S. labor and construction practices. To physically construct the fab and the supporting facilities, TSMC needed contractors experienced in chip fabs. In Taiwan, they have trusted contractors who can build a fab in a blink of an eye by industry standards. TSMC often boasts of its construction speed. In Arizona, TSMC assumed construction would be straightforward. It wasn't. "We thought that since the United States is so big, building a house is not a big deal." Wrong, Wei quipped in a talk. The local construction workforce had never built a leading-edge fab like this. Many workers didn't even know what a cleanroom production line entailed. TSMC discovered that the pool of skilled labor was insufficient, so they ended up recruiting half of the construction workers from Texas, essentially importing workers from another state at higher cost for their expertise. Even basic things, like complying with US safety standards and dealing with trade unions, were new experiences for TSMC's management. Wei noted that labor unions introduced delays and complexities TSMC wasn't used to. The CHIPS Act funding required union labor or prevailing wages, ensuring high labor standards but also higher costs. And about those costs, nearly every aspect of fab construction and operation in Arizona has proven more expensive than in Taiwan. Morris Chang, TSMC's founder, bluntly stated that making chips in the US may cost 50% more than in Taiwan, and in the Arizona fab's case, it might be closer to 100% more, double the cost. Multiple reasons drive this. US labor wages are higher. Productivity in this specific domain may be lower initially. Building materials and cleanroom components can cost more when sourced in the US, and the new supply chain lacks the economies of scale of the Taiwan cluster. A Nikkei Asia report revealed that several suppliers' own Arizona projects were halted or delayed because construction costs ballooned to 4 or 5 times what they would be in Asia. Executives from chemical suppliers were shocked at how expensive it was to build in Arizona, far beyond their initial estimates. For example, companies like LCY Chemical, Kanto PPC, Topco Scientific, and Changchun, all key materials suppliers, bought land in Arizona to support TSMC and Intel, but by early 2024, they hit pause. Some projects were scaled back, others delayed indefinitely. The flood of simultaneous construction, TSMC, Intel, and others all building at once, led to labor shortages and surging wages in the construction sector. It's a classic bottleneck. You can throw money at it, but skilled tradespeople and specialized contractors can only do so much at a time. The result of these supplier and construction challenges has been schedule slippage and cost overruns. Initially, TSMC planned to start production by 2024. By mid-2023, they announced a delay to 2025 for volume production, citing lack of skilled workers and other setbacks. Eventually, with extraordinary effort, they did manage to produce the first test batches of 4-nanometer chips in late 2024, but volume production ramp is still ongoing. Intel's own new fabs in Arizona also fell behind schedule for similar reasons, indicating this is an industry-wide growing pain, not just TSMC's issue. From TSMC's perspective, having to import everything, from materials to manpower, defeated the idea of quick expansion. In Taiwan, they can build a new fab in approximately 2.5 years. In Arizona, Wei notes, every step took longer. The compliance process alone dragged things out. It has taken at least twice as long as in Taiwan, he said. This is one reason Wei publicly stated that the latest, most advanced chip technologies will debut in Taiwan first and likely stay in Taiwan longer, because copying them to the US is so slow and complex. The distance from TSMC's R&D center complicates it as well. Their most skilled scientists are all in Asia, able to quickly troubleshoot yield issues on the spot. Fabs in Phoenix can't get that same on-demand support due to geography. Yet all these hurdles could be overcome in time. TSMC's Arizona venture has effectively pressed fast forward on building a new chip ecosystem in the US. Suppliers are coming, local talent is being trained, and infrastructure is being put in place to mimic the Taiwan cluster. The Phoenix area is even marketing itself as the Silicon Desert, with plans for a gigantic surrounding development, Halo Vista, a $7 billion city within a city, including industrial parks and supplier hubs around TSMC's campus. In an optimistic scenario, A decade from now, Arizona could have a self-sufficient semiconductor cluster, not unlike Hsinchu Science Park, albeit at higher operating cost. But getting from here to there is the tricky part. As one industry observer pointed out, it's baffling that TSMC was caught off guard by issues like permitting, unions, and supplier gaps, all foreseeable. A TSMC shareholder vented that these should not have been surprises for a world-class company, suggesting perhaps TSMC tried to move faster than prudent and is now learning the hard way. Regardless, the company is adapting. They've brought on US supply chain experts, partnered with ASU and local colleges to create a talent pipeline, and they continue to ship boatloads of gear and materials from Taiwan to bridge the gap. Wei remains confident that the Arizona fabs will eventually produce the same quality chips as Taiwan. It just might cost more and take longer to get there.